I am here with Bart from Cleverscope. You've seen before, but we've got a new...
We have a new product here, we do, a new Cleverscope.
Tell us about it.
Okay,
Looks funky.
It's very big and chunky compared to our old one, which is sitting over there.
Yeah, that's the original one.
That's the original one, yeah.
Last time. I love the PCB front panel.
Yeah, well, that's it, yeah, the gold edge. Yeah, it's 4 channels.
Yep.
It's 500 megasamples at 14 bits.
At 14 bits?
14 bits.
And it's New Zealand
bits.
Sorry, I couldn't resist.
Yeah, fair enough too. It's an isolated channel oscilloscope.
This is what I'm excited about.
So
it is fully isolated. Each channel is isolated.
Each channel has got a kilovolt isolation between itself, the other channels, and ground, plus or minus a kilovolt.
Beautiful. Hence why we're measuring a motor drive here.
We are. We're probing the innards of a motor drive.
Fantastic.
And we're looking at the gate drive and also at the saturation voltage of a transistor that's inside the gate drive, which is going up and down 320 volts. There, it's all rather noisy.
Yep.
Here is the voltage that's driving the gate, and it's through a little resistor which goes to the gate itself, which is that signal there. So we're looking across a resistor, which is going up and down 320 volts in a few nanoseconds.
Because you can measure across the resistor because you're isolated and floating.
Where there's 2 requirements here. The first is that it's isolated and floating, and the second one, the very important one, is that it has very high common mode rejection ratio.
Yes, what are you talking about? Throw some figures at us.
Well,
CMRR.
CMRR, which is how much noise gets into the measurement from the rapidly slowing signal.
Yep.
It's 100 dB at 50 megahertz.
At 50 megs?
At 50 megs.
Nice.
So
how fast does it fall off after that?
It will carry on pretty linearly after that. Unfortunately, my little test rig only checks up to 50 megs.
Right, and what's the bandwidth? What's the actual analog bandwidth?
200 megahertz bandwidth. There's a graph of CMRR over frequency. We got a 65 megahertz, and there's the 100, so we're actually a bit below 100.
Beautiful.
Which is not bad. And we can see the effect of that over here. We have a full bridge. We're going to sweep around a lot. There's a full bridge. And what we're doing, I'll point at things. We're looking at this gate here, which is connected to a switching node, which is switching between 0, which is the bus, and 500 volts.
500.
And 500.
Nice.
And over here is another gate, which is doing the opposite, between 0 and 500. And we've also got 2 probes looking at the actual switching voltage, so we can see what they are.
Do not do that with a regular scope, people. I've done a video on how not to blow up your oscilloscope. That's a way to blow up your oscilloscope.
That is
Trust me.
Very good way to blow up a lot of stuff.
Except if you've got an isolated scope, isolated channel scope like this.
Exactly.
Yep.
So here we have a graph. You can see the connections here. The 2 red probes are the switch voltages, which are going 500 volts, and the 2 grey probes are connected to the gates.
Got it.
And here we can see the red one is the 500 volts, and it's switching. You can see that it's about 506 volts. It's switching in 8 or 9 nanoseconds. So it's quite fast.
That is very fast, yeah.
Right. Then these signals here are those 2 gates.
Nice.
They're sitting on top of the 500 volts, 0 to 500 volts.
Yep, and we can see some switching component when it transitions.
We can go and investigate. Okay, so here...
Oh, so we zoomed in. This is a zoomed in view,
this is a zoomed in view. So this is looking at that spot there.
Yep.
So we're looking at that and that.
That looks sharp there. That looks like a nice
Well,
edge, but it's not.
But it's not.
There you go.
No. It's the gate turning on. This is, but this is the Muller plateau. And that's the voltage level at which the voltage stops rising because the charge is going into the gate like crazy. Okay, now there is a problem with FETs, which is what this is. These are FETs, in that there's a capacitance between here and another one between here and here.
Yep.
And that capacitance acts like a voltage divider. And as you raise, and the effect of it is that it's like a capacitance from the gate down to the negative bus. As you're raising the voltage, and the opposite way around when you're reducing the voltage, and that tends to suck charge out of the gate drive. So this reduction here is a reduction because of the Muller capacitance.
Got it.
And this pulse here is because the Muller capacitance is injecting charge back into the gate. These can be problematic if your design's no good, because if you make this too low, in fact below 4 volts, it will turn the FET off.
Of course, yes.
And if
Switch
you
it back
go
on, and bam, it goes. Yeah,
it's
that'll
not
ruin
good.
your day. No.
No. Same here. If this goes above 4 volts, you start getting a little bit of turn on in the FET.
Yes.
Then you have 2 FETs on at the same time.
Oh,
Is that a good plan?
You get feed through on your power rail. They short out.
You do.
Yeah.
They do. Happily, FETs are actually pretty rugged.
Yes.
And as they get hotter, their resistance increases, unlike IGBTs. And so you are a little safer, but it's not a good thing to do.
Yep.
The losses go up. Don't do it. But the big thing is that this is almost impossible to measure using any other method. You could buy a Tektronix TIVM probe,
What's that?
$13,000.
Oh, is that the new fibre optic?
Fibre optic
The new
isolated
fibre
one.
optic isolated,
You could
yep.
use one of theirs, which does the same thing,
Yep.
except a bit noisier.
Right. At the bandwidth?
At the same bandwidth.
What's the bandwidth of that?
Theirs is 200 megahertz is their lowest cost one,
Right.
only $13,000, and they have a gigahertz one as well, which is only $23,000.
And it's just a probe.
It's just one channel.
It's just
one
channel,
probe.
One probe.
That's right. We have 4.
Yep.
Okay. No other way of measuring this.
Does this come with high voltage probes?
It comes with every probe you need. So we give you 4 low voltage, 1 switched 1x10 by probes, and 4 high voltage 100 times probes.
Nice.
And if you really want, we can give you 200 times probes, because then you can look at 1.6 kV.
Ooh, excellent.
Yes.
Excellent. But most MOSFET solutions stop at around about 500-600 volts, something like that.
That's
kind of.
right, but
when you go above that, it's a bit more special.
there's a lot more technology coming along. They have things called SiC. Have you heard silicon carbide FETs?
I have silicon carbide FETs.
Okay,
yep.
they're rated at 1200 volts.
Nice.
And people are starting to use that 1200 volts.
I don't think they were around when I was doing 500 odd volt MOSFET design.
No, not at all. They're new. They're new.
Yeah, this was like 12 years ago, mate.
And they are tricky, because you can get edge rates down to about 3 nanoseconds. Horrendously fast.
That is ridiculous.
Well, then you have to deal with lots of other problems as well, of course. Any series inductance, massive ringing voltages, you don't want that. Any EMC issues you might have, well, they can be magnified.
Forget it. When you've got 1500 volts switching in a couple of nanoseconds, your EMC's out the window anyway.
Exactly.
So,
even this is a bit fast.
Yeah.
Exactly. I mean, 7 to 8 nanoseconds or whatever it was. Yeah, it was 7 to 9, I should say.
Yep.
It's pretty damn fast.
So that's impressive. So how much does this cost?
Well, this one, the Wii is $9,600.
Yep.
Moderately
Aussie
expensive.
or Yankee bucks?
Yankee bucks.
Okay.
Yeah, pretty expensive, but we are open to deals.
It's a specialised bit of kit.
It's a specialised bit of kit, and as I say, you can buy a whole one for less than the price of one Tech probe.
Is there any other competition for an equivalent 4-channel isolated scope?
No.
On the market? No?
There's no other competition.
Tech have an isolated scope, but it doesn't go that
The
high, right?
The TPS series scopes, they're isolated, but they're only 300 volts isolation between channels, and their common mode rejection is about 30 dB at 10 megahertz.
Oh,
So 30 dB is like 1 to 50. So if you're looking at 500 volts, you'd be 10 volts of common mode noise whacking around here. You wouldn't see that signal with 10 volts of common mode noise. So that's the big deal.
Wow, that's
the big deal.
Yeah, because we're down on a scale there. Yeah.
Oh yeah. Look at that. Yeah, that's right.
If we had 10 volt of noise on there.
If we had 10 volts of noise, you couldn't see anything.
Wouldn't see it at all.
No.
Wow.
No.
Impressive.
And the same goes for differential probes. Differential probes are also used to try and do this job, but they also have terrible common mode rejection ratio at high frequencies. They're great at 50 hertz, but once you get them up to 10 megahertz, they're useless. These 8 nanosecond slew rates, well, their equivalent bandwidth is 1 over pi TR. So that's 1 over about 3 times 8, that's 1 over 24, which is about 40 megahertz, So that's the equivalent of a 40 megahertz signal. So you have to have pretty good common mode rejection to reject it and not see it in the signal.
For sure.
Yeah.
All right, can we take one of these apart?
Yes.
You can show us how it works.
Yes, we can.
You can explain the design and everything.
I can.
He's the designer.
All right.
He doesn't just sell them.
Oh no, we
All right,
we do everything.
We're going to turn it off first.
But we're going to turn it off because there's lethal voltages in here.
Yep.
Okay, so we're unplugging things.
And we're going. All right, Bart, tell us about this.
Tell you about this, right.
Sorry, I just want to see the isolation slots down in. Oh, yeah, they're actually, I can see the slots. Look at that. Each one is a massive, what'd you say, a 1500 volts isolation?
Yeah, it's 10 millimeters, which under the IEC standard, it's about 8,000 volts of real isolation, but in terms of meeting the standard, gives you 1,000 volts, category 3. Yep, so it's pretty good.
Sorry, we're not going to be able to open the cans today.
No, we are not. No, that's quite a drama, opening the cans.
All right, tell us all about it.
Okay, I'll tell you all about it. So these are the 4 channels. They're isolated from each other. As you can see, there's a fiber optic link here. These are there's actually 4 fibers in there, and they go at 10, they're capable of 10 gigabits per second, but we only run them at 5.
Right.
So they're 5 gigabits per second from here to here, and there's 2 channels one way and 2 channels back the other.
Hang on, where?
These things here, see those little wires?
Say, it is. Yeah.
Yeah, can you zoom in on those?
I can. I thought it was.
Yep, those are.
There we go. I couldn't say it right. The colour was a bit different.
Yeah, that's the fibre channels. You'll find that the blue ones go one way and the green ones go the other. And they're running at 5 gigabits per second.
So you've got the converter inside the front end.
Yes, we do.
Right, and you're just running the digital. I was going to ask, how are you isolating it, digitally or analog?
Digitally, because we want to minimise noise to the absolute maximum.
And so that was the best way, that was really the only choice?
That is the only choice. That's the only choice. The other guys, that's the Tectonics guys, they do it the other way. They modulate a signal and send it as light as a modulated analog signal. But the result of that is that they have much more channel noise than we do. So we wanted to keep the channel as quiet as possible, and the only way to do that is to have as few bits in the way as possible. Yep. That's what we do. So
that's a 14-bit ADC.
14-bit, 500 megasample ADC plus some, and then this is the power supply that runs it. Now, power supplies are actually really tricky.
They are. You've rolled your own by the looks of it.
We have rolled our own. Now the big issue with this, and I'm giving away trade secrets here, but it's so much better that everyone knows, is that this power supply here has very low common mode noise going out into the real world. It's less than 100 microvolts.
Nice.
So it doesn't need bootstrap capacitors to link the input to the output to route the noise back to the input.
Right.
And it's driven with a very symmetrical power switch. It was hard work. It took us a year to design this. A year to design just the power supply.
I can believe it.
Bloody terrible. Okay, and then as we carry on, you'll notice that we have got 2 fibers one way and 2 the other. Well, one of those fibers we use for a clock, a very accurate clock. It's a half a ppm clock.
Nice, that's pretty good.
Yep, and it's only running at 500 kilohertz, and it comes into each device, and it's distributed using a. No, you can't see it. It's on the back side. It's distributed with a very low latency clock.
I was going to say, are there any synchronization issues across the channels?
There's a lot of synchronization issues across the channels. That's another really hard problem. We wanted to be able to make it so we can use this device for our frequency response analysis system. Yes. I don't know if you've seen that, but it means that we can do gain phase.
I've got the Bode 100.
Right. Yep. We do the same as the Bode 100, basically.
Excellent. Right.
Yep.
But with fully isolated channels.
channels.
That's handy.
So you can go and fully isolate a signal generator. So
it's isolate. Yeah, you've got the same.
Same thing. Yeah, that's right. Yeah, you do it in one place, you might as well do it in the other.
Excellent.
Yeah, so that means you can inject a signal into the error amplifier in your live power supply and measure live things.
And the full frequency response of your 1500 volt.
Exactly.
Power supply. Wow.
That's right.
There's nothing on the market that does that, surely.
There is nothing on the market that does that.
Except this.
Quite right.
Excellent.
Okay, so we have these clock signals coming back so that the error between channels is about plus or minus 70 picoseconds. Pretty small.
Very impressive. Yep. I wouldn't have thought that would be a necessary requirement on a 4-channel scope like this, but when you say frequency response analysis...
Well, you want very low phase error.
Yes,
because if you want to measure things like inductance or capacitance, you need to have good accurate phase.
Indeed.
Yes. So here are the 8. There are 2 lanes in each direction, so there are 8 lanes coming into the FPGA. This is an ARIA 5 FPGA, so it has 8 lanes coming into it.
That's a pricey FPGA, isn't
It
it?
is a pricey FPGA.
How many pins?
It's
How
got
many balls?
960.
That has a lot of balls, that chip.
It has a lot of balls.
All right.
That's right. It's a very ballsy chip.
Tell us about the choice of FPGA. Did you need it for the... You obviously didn't need it for the I/O count.
I did actually, because
did?
you might notice that this board plugs into this one, and it's using the equivalent of an Altera daughter board connector. Let's call it that.
Oh, yes.
Okay, it's their standard connector. It's high bandwidth, and we plan to offer more digitizer boards that you'll be able to plug in. And one of the digitizer boards we want to provide is a 4-channel 1 giga sample per second board.
Wow.
Which is based on a E2V chip. It needs lots of parallel lines.
Got it. Okay.
Lots of parallel lines.
Yep. So you've got it for the I/O plus the transceivers probably.
Exactly.
And did you use all the gates, or did you you've got a low?
No, we've got a
gate
lot of
count?
spare gates
Yep.
because it's upgradable in the field, and we plan to add more value over
Is it
time.
upgradable via the USB interface?
Yes, it
or
is.
whatnot?
Yep.
Excellent.
Yep. So we have it supplying application, so you can just upgrade it as you go
Fantastic.
in the field for no extra cost. So then the other things down here, there's a power supply system, which there's lots of power supplies you need for an ARIA 5, sadly.
Of course, yeah, you need like 5 different rails.
Yeah,
It's really annoying.
you know, like 1V1, 1V15, 1V2, 1V8, lots of them. Nightmare. And this is our I/O board, and we have an isolated signal generator, 0 to 65 megahertz. And you can see here the 2 isolated transceivers that allow us to get signals across the gap. We're not actually using fiber for them. These are pretty good.
Okay.
Low capacitance.
Yep. So that's a matching 14-bit one, is it? Or?
It is.
Yep.
It's a 14-bit one, and it samples out at 170 megasamples.
Nice.
So it's a little bit slower in sampling out, but it still does a pretty good job.
Is that full arbitrary capability?
It is. It's got a 4K arbitrary buffer, so it's not huge,
Okay.
but it still can do quite a bit.
Is that done inside the FPGA?
No, the problem we have is
right.
it's isolated.
Of course, yes. So you've got a little FPGA under there.
No, we use an analog devices chip, which has an arbitrary waveform generator built into it.
Got it.
Yeah, so it's very handy.
Terrific.
And that gives us a frequency range of 0 to 65 megahertz. Yeah, with very low distortion. So the whole system is very low distortion. So we do better than 80 dB
Nice.
down, which is not bad. And then here is the USB 3 connection, and we're using an FTDI chip there for the USB 3 because it also supports USB 2.
But so you need USB 3 for the bandwidth, for the data?
We have a lot of data coming backwards and forwards. Yep. And we also do streaming. So if you want to stream to disk, you need high bandwidth, especially you've got 4 channels at 14 bits each.
Does this have any local storage at all? Is there at 100, or is it like 100% streamed via USB?
No, the USB is far too slow for that.
Right.
Okay, so if you think about it, it's got 500 megasamples at 16 bits essentially.
Yep.
Okay, so that's like a gigasample. That's 4 channels. So that's 4 times 16. Let's call that 2 bytes. 4 times 2 bytes is 8 bytes. Times 500 megasamples is 4 gigabytes per second.
Oh, yes.
You cannot get 4 gigabytes per second across a USB link.
Bytes, not bits.
Bytes.
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 Yep. Awesome.
Yeah, not
so
bits.
how much storage does it have?
It has 64 megasamples of storage.
And you're
for
doing
all
that
the
with these babies here?
We are, and there are some on the other side as well.
Oh, okay, yep.
So we turn it over, we can see another 2 there. So that gives us 64 megasamples for every channel. So there's 4 channels of analog and 1 channel of 8 channels of digital.
How long does it take to dump that full memory over to the PC if you use the entire acquisition memory?
If you dumped a whole lot over USB 3, at USB 3 we're getting about 200 megabytes per second. Okay,
So
So
like 10 seconds or something.
Yeah, something of that order.
Right.
So that we don't work that way.
Right.
What we do is we just decimate out 10K samples
Yes.
at whatever rate you need to fit the screen.
Because we saw on the screen before, we were getting like real-time update in there, so it's just a lower sample.
It's a lower number of samples.
Number
Exactly
of
right.
samples,
Yes, but you can get the whole buffer into memory if you want. You just have to wait. And we stream at about 3 to 5 megasamples per second. 5 megasamples per second, and that can run for weeks if your hard drive's big enough.
Got it.
And we provide the tools so that you can zoom around in it and do FFTs and protocol decoding and maths and lots of stuff.
With the software, does it support like big 4K screens and you can see all the full 14-bit?
Yeah, it's just Windows.
There? It's just Windows.
Just Windows.
Zoom it. Nice.
Not a problem.
Yep.
This is an SFP socket, which stands for Small Form Factor Socket, and it's so that we can plug in an Ethernet module.
Nice.
And
why didn't you just put Ethernet on there as like just an Ethernet?
Because a lot of our users would like to have fibre.
Oh, of course.
And
Right.
instead of copper.
Yes.
And then you can see these are the two sorts of modules. So
Right.
this is a wired 1 gigabit per second Ethernet module, and this is a fibre one.
Yep.
Fibre is quite common, you see, and we would have to use up a lot more real estate to put both in there.
You obviously can't, even with 1 gigabit Ethernet, you can't stream the full buffer in real time.
You can't.
Can you do it with fibre?
No.
No, you can't.
4
Okay.
gigabytes per second
Oh, okay. Yep.
is 32 gigabits per second.
Gigabits per second, yeah, okay.
32 gigabits per second.
It's just not going to happen.
No.
Fantastic.
Even 10 gigabits per second wouldn't do it for you.
Who are your main customers for this sort of kit? Because it's not cheap. It's it's $9,000, but it's the only thing on the market that does the job.
That's right. So our main customers to date are the people who work in power electronics. And power electronics is becoming more and more ubiquitous because it's used in electric cars.
I was going to say automobile manufacturers, they
exactly.
don't have one.
So we have them at Bosch and Siemens, and we're trying to work with Delphi and Delco in the States, who are also making engine controllers and things like that. So yeah, the people who use it are people who are mostly into power electronics, which is part of the green tech movement, which we see as being a growing market.
Because you wouldn't buy this as a general purpose scope.
No.
You still sell the old one as like a general
We
purpose
absolutely
scope?
do. That's a general purpose scope. It does all the same things, the frequency response analysis, the streaming, the maths, all that sort of stuff.
But it's not as...
bandwidth is a lot lower.
How much is that these days again?
It's about $1,000.
About $1,000, yeah.
Yeah, so it's
Is
still
it
more...
the same software?
Yes,
on both?
exactly the same software. And you can link the two together if you really want to.
Nice, yep.
Some limitations, but that's how it is.
Terrific.
Yeah.
And this has been out for a while now, but you're still sort of always refining it.
This has been out for about a year in the form it's in, but we are bringing out an entirely new board set, which doesn't fix any serious deficiencies, but makes some things that we want to do better.
Any other design gotchas on this that caused a real headache during development? Was the front end an issue?
The front end is a
meg front end, or is that easy peasy these days?
No, that's probably why we're having a new board for the front end digitizer.
Right.
One of the issues is that if you've got a 14-bit converter and your channel noise is only two LSBs, so like if you're looking at 800 volts, you're getting 200 millivolts of channel noise.
Yeah.
You really want to maintain that over the entire frequency range, don't you?
You do.
You do?
Why not?
Okay. Now, one of the big issues we have is probes. Probes themselves are not linear to that degree. They might be good for 1%, so 1 part in 100. We want 1 part in 8,000.
Exactly.
So that means if you're looking at a square wave, we want the top of it to be linear to within 1 part in 8,000, just 200 millivolts actually, what we're aiming for on 800 volts, sorry. And we found that we could not get that with standard probes.
So what was the solution?
The solution is we're working with Pentec, who make our probes.
Yep.
and we have modified the probes for them. We've changed their probe design.
So you actually said, can you design it this way and this way?
Well, they haven't done the design, we've done the tweaking.
Oh, you've done the tweaking.
And we're handing the design across to them to make. That's
so
right.
They handed over their base design and you said, well, and you mucked around with it. And
Exactly, and in the process of doing that, we also had to change our own front end design. Our front end still works perfectly well with the standard probe, but what we've done is we've matched the characteristic of the Pintec the probe with our front end, so they beautifully match across the whole frequency bandwidth, and they give us 1 part in 8,000 linearity.
So what did you have to tweak to do that? And why don't they do it on standard? Well, I know why they don't do it on standard probes, because they don't have to.
They don't have to.
14-bit converters.
No, 8-bit converters, you know. And you've probably got two bits of LSB noise as well. It's only 1 in 100 is all you need. And if I try and do these sorts of tests with my tech scope, I can't even see it.
Yeah.
You know.
So what were the little tricks that you had to do, or is that secret squirrel?
No, we ripped apart their probes, and we discovered that we had to add in a couple of little extra capacitors and a little inductor to match the poles and zeros that shouldn't have been there. And in our own front end, we found that when we switched ranges, that we weren't having beautiful impedance. Keeping the impedances exactly the same, so we've had to add an extra little switch that switches in a bit more impedance so that both channels are exactly the same.
Got it. Now, probe designs are usually, you can either get top probe compensated up here or compensated down there. Which one did you go with?
This is compensated down here.
Oh, right.
It's isolated.
Hold on there.
No, that's right.
So there's no trimmer, you can't trim it?
You can. You have to undo that label.
Oh, right, okay, it's under the label.
It's on the label. It's like this idea, though it's down there, you know.
Oh, okay, I see.
But it's got a little plastic hoogery flickery.
Alright.
So it's like that, except I've put it under the label so that people don't twiddle with it.
So you had to add the stuff to the probe?
Inside the probe.
Yep, inside
the
probe.
No, it's actually down this end. This is where all the action happens.
Yep.
Anything up here has to then contend with the impedance of the probe coax cable.
Of course.
And it's much easier to do it on this end. So that's where we've had to do it. That's right.
Got it.
And then our own changes are in the front end here.
Got it.
Yep.
Are they allowed to sell that probe to anyone else, or is that your own custom?
Well, they could, but it's a little more expensive for them to make. So I doubt that they will.
Right.
Because it won't match the other people's stuff.
Yeah, but you can sell it just based on spec, can't you?
You can. You can say this is a way better probe, yeah.
Well, a lot of the scopes are coming out as 10 or 12-bit now. So a lot of the high-end, Keysight and Tex and Rode.
Yeah, I know, but they say they're 12-bit scopes. But if you go and look at the actual effective number of bits, it's still down at about 8.
It's not terrific.
No, so it's true they are 12 bits, but the noise is still pretty high.
Got it.
We are an order of magnitude better noise. So yeah.
Terrific.
That's life.
Awesome. So are there any other really troublesome things that caused you heartache during the development?
Let me think. In the front end, yes, there have been lots of hassles in terms of components not working the way they should work. We started off life using, well, we still are, using some analog devices, op amps, and the spec for the op amp is that you can power it down, okay? Yeah. But when we powered it down, it dragged the input to -5 volts. And we didn't expect that, and neither did the designer who I spoke to in Ireland, a woman who said, no, it doesn't do that, but then when she went and checked it, it does. Bugger.
Wow.
The second problem that we had is that it has an output that you are supposedly able to multiplex. So we have two ranges, the 800 millivolt plus or minus 800 millivolt range and plus or minus 8 volt range. And we wanted to multiplex between the two ranges, and we're going to use two op amps and switch one off and switch the other one on. And I talked to the designer and she said, yes, this is going to work fine. You'll all be fine. We design it. Guess what? It wasn't all fine. No, there was leak through even when it was off.
Wow.
So
okay.
that was a problem for us. So, and then we've discovered the ADC that we use is actually inside its two ADCs. They're two 250 megasampled ADCs, and they interleave them.
And they interleave them.
They do.
And what? And they don't tell you that on the data
Oh no,
sheet?
they do.
Oh right.
They do.
Okay.
And they have this engine. They call it an engine, which tries to get the gain and phase correct so they interleave beautifully.
Yeah.
But it turns out that they did all their testing only in the RF domain on sinusoidal signals. And when you put in a non-sinusoidal signal, when you put in a single-ended signal that may be just the bottom of an edge, the whole thing turns to custard.
Oh.
It took us a lot of effort to overcome that. We've been working with Intersil to try and fix that.
They're not Intersil anymore.
No, they're now Renesas.
Yes.
Yes.
They dropped the name officially.
Yes, they have. They're no longer, but the guys inside are still Intersil guys.
Still there. Okay.
Yeah, that's
Awesome.
right. Yeah. So that was a little hassly. Yeah.
How much total? How long did it take you all up to do this from go to woe?
Well, I reckon it's been about 4 years.
4 years,
which
I
is
can believe
huge.
it.
Yep, 4 years.
How big's the design team?
3.
Is that for working on it full time for 4 years?
Two of them. See, one of the guys is doing all the application software,
Right.
and one of the other guys is doing all the hardware, and then I do the FPGA and the C inside this thing here,
Yep.
and I don't have full time available, so no, 2.5.
Sure. Well, that's impressive. Thank you very
Yeah.
much, Bart.
Well,
That
it's
is
very nice to
awesome.
see you again.
Thanks, mate.